All right, hey guys. So I was thinking the way we can do this is I'd like to take questions from you right now, uh, and then I'll kind of like try to figure out everything like what everyone wants to talk about, and then plan accordingly. And I was thinking basically we'll have a little break after the first hour, so around like 6 o'clock, and then and I'll do kind of the same thing again at that point, basically. So I'll sort of take a second round of questions then, just for like general questions, basically. So if you have any general questions right now, then this is the time to ask them. Actually, hold on one sec. Let me pull up the participant list. Okay, yeah. So yeah, if you have a question, do try to use the hand raise feature, please, since there are like quite a few people here. That'll prevent chaos. So any questions? Okay. Well, in that case, then I guess we can just sort of go through the review problems. Let me think. Yeah, sure. So let's go ahead and just like go over the review problems for now, and then like I said, I'll stop again and take any questions if you think of any. So the first let's see. All right, so the first review problem was this. So suppose an is L, from I guess n equals 1 to infinity. Then must we have that the sum from n equals 1 to infinity of a to n minus 1, oops, plus a to n equals L, right? Yeah. And also, like, what about the converse? Well, let's just deal with the forward statement as it's written first, right? So what do you guys think? Does anyone have an idea about whether or not this is true? Well, let's think about the partial sums of the second series, right? So let's say, Sn is like the sum from k equals 1 to n of an, or I guess, sorry, ak. And like Tn is the nth partial sum of the second one, so k equals 1 to n of a 2k minus 1 plus a 2k, something like that, right? Then Tn is just S2n, right? So Tn, the sequence of partial sums of the second series, is just a subsequence, right? So is a subsequence of the of Sn, right? Of the sequence of partial sums of the original one. So it has to converge, right? So it converges to the same limit, right? So how about the converse? So say we know, right? Say we know this. Does the original series have to converge? Any takers? All right, tough crowd. Maybe for some of the future problems, I'll actually like give you guys a minute or two to think about them first. Okay, so this is false, right? And like a very simple counterexample would be like an is -1 to the n, right? Then the sum of these this one where two terms are added together at a time is just the sum of 0, right? Because this is -1 to the 2n minus 1. This is -1 to the n, which is 0, right? Or sorry, -1 to the 2n. So this is just -1 and this is 1, basically. Right. So this is just 0, but the sum of an does not converge, right? As we've seen before. So are there any questions about that?
Could you clarify for the first part? Sorry, why is it a subsequence of the?
Yeah, because so the nth partial sum of this is just the 2nth partial sum of the original series, right? So if you add together n terms of the second series here, it's the same thing as adding together the first 2n terms of the first series, right? So what I'm saying is Tn is S2n, right? So that just means that the Tn's are just like the even numbered terms of the sequence Sn, right?
Got it. Yep.
Any other questions? Okay. Yeah, so the second problem was so something like this. Suppose, and sorry, I had to like transcribe because I forgot that my Zoom like whiteboard for some reason it's like impossible for me to look at stuff to like change windows. It stays on top of everything, so I had to like transcribe all the problems really fast to like my notepad, my physical notepad right here, and so I might have to like pause for a sec to remember some of the details of the problem statements, but So I think this one is like this. So it goes like, suppose this power series, aka x to the k, from k equals, I guess, well, I guess it's not given. Doesn't really matter. Uh, has radius of convergence r, right? Then does this series converge uniformly on negative r r? Oops, open. Right. So for those of you who haven't had a chance um, to look at the problems before coming here, I do want to give you guys a little bit of time to work on it. So I want to make sure we get through like as many of the problems as possible. So this won't be like a really protracted affair, but I would say let's take like 3 minutes. So I'll come back in about in 3 minutes, and we'll talk about this. Okay, and we'll kind of do that for as many of the problems as we can. So I want to give you guys a chance to think about it. All right, so we'll resume at 5:20. All right, so uh, what do you guys think? Does anyone have an idea? Yeah, Wei Shi.
Oh yeah, so I think it's false because it must be continuous, but it can be like not uniformly continuous, right?
Yeah, that's basically, I think that's basically correct. But like so justifying it using like uniform continuity is a little bit harder because it's not
Uh-huh.
from the fact that, like, suppose that the power series, the function that the power series represents, is not uniformly continuous. It's not actually immediate just from that the convergence isn't. Uh,
Okay.
but you're definitely like thinking on the exact right track, because any of the examples, I think any of the common examples that you can pick for this will be like non-uniformly continuous functions.
Uh,
Yeah, like I think probably. Oh, is there another? Oh, okay, never mind. I think. Yeah, I think. Yeah, just something like the sum of like x to the k from k equals 0 to infinity, right? This is 1 over 1 minus x. Um, and this has like radius of convergence 1. This does not converge uniformly on -1, 1 because, right, I've kind of mentioned this exact example before, I think. But if you remember, right, one sort of quick way to be able to like see why, like, this is not a fully detailed, you know, honestly, if you wrote what I'm about to write here, I think I'd probably just give you full credit, um, because it's not too hard to go to justify it. But yeah, so basically, 1 over 1 minus x is not bounded, right? But each partial sum from k equals 1, like 0 to n of x to the k is bounded by, k, let's say, or sorry, n, right? So the fact that each partial sum is bounded, but the actual, target function here, 1 over 1 minus x, the function that this infinite series represents, is not bounded, means that there have to be some values of x for which like the difference between this function and whatever partial sum you're looking at is like arbitrarily large, basically, right? So it's kind of immediate from that the convergence cannot be uniform. Okay. So any questions about that? Okay, so, and also remember that like, so the convergence actually is uniform. So this is like a side thing. The convergence here is uniform on any like negative a for 0 less than a less than 1, right? So that's always been kind of a difficult thing for a lot of people to really wrap their heads around, but that the convergence is uniform on any strictly smaller closed interval, but it's just not uniform on the entire interval from -1 to 1 simultaneously. Okay? Okay, so yeah. Let's move on to the next question. So this is...
I think someone has a question they're sending on chat.
Oh, sorry. Oh, yeah, maybe we can't hear. Hold on. Let me open the chat. Oh, okay. Yeah, sorry. I couldn't hear you. Yeah, I'll keep the chat open. I'll try to keep an eye on the chat from now on. So if you can't, if for whatever reason you can't seem to speak up, then you can send a message in the chat. I should be able to see it. Okay, review question 3. All right, so let's say, so it's a give an example of a sequence fn of functions on 0, 1, such that fn goes to 0 pointwise, but not uniformly on 0, 1. Okay. So yeah, again, we'll take another 3 minutes. So let's resume at 5:30.
Wait, quick question. Hello?
Yeah.
Yeah, sorry, I think while others are working on it, back on the previous problem, since n, how come that's like justification enough, like that is bounded by n? Because n is also growing unboundedly, right?
But right, the point is that that doesn't matter basically, right? Because for each one, like if you just fix a value of n, right, then n is just a number. So the partial sum is bounded by n, right, in absolute value for all values of x, right?
Yeah.
But this is not bounded at all. So like the point is that here, let me draw a picture. Right? It's like here's n, and I don't know, whatever, negative n. Right? Here's 1, and the the series is like doing this, or like the true function, right? That's like 1 over 1 minus x, right? And the other function is stuck, right? So fn is stuck in between these two lines for all values of x, right? So if you look at these values of x, right, the error between f of x and fn of x is unbounded.
But n is also going to infinity, right? So then,
But no, because we're just fixing a single value of n, right? But just
oh,
fix a
okay.
value of n. Is it true? So fix n. Is it true that absolute value of fn of x minus f of x is, can be, made, well, okay, sorry. This is awkward phrasing, but
Yeah, that's unbounded.
yeah, this is unbounded. So there's no way to make it, no matter what n you pick, right? No matter how big you make n, there's always going to be values of x where
Oh,
this
okay, I
is.
see. And that's the definition of uniform continuity.
Exactly. Yeah.
Thank you.
Yeah. No, thank you. No. This is like such a common thing. It's honestly like that's exactly like what I'm trying to elicit when I put this problem out there is that exact point of confusion, because it happens a lot. So yeah. Okay. Well, anyway, so I think in the interest of time, let's just keep moving forward. So right. Yeah, so we have seen an example of this before, which is like it's in the textbook. So fn of x equals n squared x to the n 1 minus x. This works. It's not like, let's see. I believe, yeah, n squared x to the n goes to 0. Well, they justify this in here. Let me actually. Right. So, oh yeah. So they cite exercise 9.12. So I'm just going to say, yeah. There are other ways to justify this, obviously. I think 9.12, exercise 9.12 is actually very useful. I would say, like, if you ever find yourself needing to say something like n to the p, you know, x to the n goes to 0 for x, like, less than 1, right? Exercise 9.12 is, like, the canonical way you can do that without having to go through a whole mess of stuff. So clearly, so Fn goes to 0 pointwise, right? But then, like, they calculate, so it's calculated that Fn of, like, n plus 1 over n, or n over n plus 1 is like n squared over n plus 1 times, like, n over n plus 1 to the n. And this factor converges to, like, 1 over e. So this goes to plus infinity, right? So actually, the maximum value of this function is growing. It actually grows unboundedly with n, even though pointwise the function is actually going to 0. So yeah, I mean, again, this is kind of a situation where, like, the fact that the maxima of these functions grow unboundedly kind of, like, automatically means that the convergence can't be uniform, right? Because if you just look at the, like, if you're trying to force Fn of x minus f of x absolute value to be less than epsilon, the larger you pick n, the worse it's going to get, because there's always going to be a value of x where, you know, absolute value of Fn of x minus f of x is actually, like, bigger than, you know, n squared over e or something like that, right? So it's impossible to make that be less than epsilon, right? Are there any questions about this?
Question: where is this maximum hit then? Because if all of the values are pointwise going to 0, you have to hit that.
Right. So the maximum is being hit at n over n plus 1. So the maximum occurs closer and closer to x equals 1 for each n, right?
Mm-hmm.
So yeah, if we sketch, like, if we kind of sketch this, it looks something like, you know, this, right? And so basically, right, if you fix your attention on any specific x, right, if you fix your attention on a specific value of x, eventually the maximum, like the maximum of Fn, is going to move all the way past x, right? And it'll just keep getting closer and closer to 1. And then, so then x will be kind of on the tail of the function here, and that tail will keep getting, like, depressed further and further down, right? And so it'll approach, Fn of x will approach 0 for that fixed value of x, right? Remember, it's like for pointwise convergence, it's kind of like my general advice is, like, for pointwise convergence, fix x and imagine n is variable. For uniform convergence, right, fix n and imagine x is variable, right? In this situation, it's a little bit more complicated, because the point is that it's like, you still have to understand what's happening as n increases at some point, right? Because the point is that, like, as n increases, the error between Fn and f is going to 0 uniformly for all values of x, right? But the point is that it's like, because we're asserting that the error has to be less than epsilon for all values of x, then it's like, whatever fn you pick, that's supposed to be like a good approximation of f. After you pick the value of n, that's where where fn is supposed to be like a good approximation, then you have to like imagine x being variable, and you have to make sure that fn of x is close to f of x for every value of x at the same time for that one value of n that you picked, right? And it's a little bit more complicated than that because it's also like you have to actually pick a capital N, and then this has to be true for every fn beyond that capital N. But it's good to kind of like ignore that for like a second when you're thinking about uniform convergence, and just to think about like a single fn, right? For a single value of n, what is actually happening if you look at like all the values of x in the set where the convergence is supposed to be happening, right? And so with these fn's, it's like for a very large value of n, the biggest error between fn and f is actually like huge because it's at this peak here, right? But the peak is like moving around as n changes. So that's why it's like if you fix your attention on a specific x at first, then the peak doesn't matter because eventually the peak just moves far away from x, and then you just don't care. You don't care what's happening at the peak as long as at this specific value of x, the value of fn of x eventually goes to 0. Okay. Any questions? Okay, so let's move on. So yeah, so this one was give an example. And this kind of goes back to the point we were talking about earlier too. An example of a sequence fn of functions converging, let's see. Right, so yeah, each fn is continuous and bounded, yeah. For, I think, open interval 0, 1. Yeah, it has to be open because otherwise f would have to be bounded. So fn is continuous and bounded for each n, but f is continuous and unbounded. Yeah. So yeah, let's take a couple minutes. Yeah, we'll say resume at like 5:43. All right, so there's actually like there's like kind of an immediate example given the discussion that we just had, which would just be to take like Fn to be the sum from k equals 0 to n of x to the k. And f is just like 1 over 1 minus x. Right. So then each of these is bounded, but f of x is not bounded. Right. Another example would be something like fn of x is just like the minimum of n and 1 over x. So then it's sort of like, basically what this looks like is it's, you kind of chop off. So here's like n. So here's x equals 1. So you kind of like, you take the function 1 over x and then you just like chop it off when it hits n. So it's still bounded, but then it's like n goes higher and higher and higher. So eventually for any specific point x, once n gets high enough, then fn of x is actually just equal to 1 over x. So this is another pretty straightforward example. Any questions about that?
Would the sequence that we used for question 3 also be an example?
No, the problem is that f is not unbounded in that case. So it just like this sequence, this just converges. This just fails to converge pointwise. But remember, or uniformly, sorry. But remember, in this case, f of x is just 0, right? Whoops.
Oh, right, on the open interval. Yeah.
Yeah. So yeah, and in fact, yeah, it's impossible to do this on a closed interval just because f would have to be bounded no matter what. If it was continuous, if it's continuous on the closed interval, then it would have to be bounded. Okay, any other questions? Okay, Doug. So.
Oh, wait, sorry. Can you go back to the slide
Sure.
that you were just on for a sec? Thank
Mhm.
you. What does fn converge to in the second?
Oh yeah, so f of x would be 1 over x in this one, right? Because it's just like, eventually once n, if you just take the limit as n goes to infinity here, eventually you just get 1 over x over and over again.
Right, okay.
Yeah. Okay, so yeah. So for this one, we have this function f of x equals x e to the minus x. And the problem is to show that there are exactly two, right? It is exactly, right? Yeah. Two solutions to f of x equals 1 over pi. Okay, so yeah, let's resume at 5:50. And the hint is to try to use the intermediate value theorem somehow. All right, so let's take a look at this. Sorry, I know these are like pretty rapid fire, but I think probably if you haven't worked on these before now, then I guess I would say that to get the most out of this, you should try to think about the problems on like a high level if you can. So sort of like try to figure out like what your main strategy might be, or like think about a couple different possible like overall strategies for like how you might try to solve the problem, and then sort of compare that to like what I end up doing, I guess. So yeah, and one thing here, I mean, obviously for x, that for negative values of x, f is just negative, so there are obviously no solutions there, even if we define f for that too. In the problem as it's stated, it's just for x in 0 to infinity, but in either case, it doesn't matter. So we can just consider what f looks like on this range. So it's something like this is the picture, right? And so the idea is that it's like, okay, here's like 1 over pi. And we want to kind of like translate our idea of what it looks like into an actual argument. So here's what we can say, okay? So f of 0 is 0. And if you do some scratch work in the background, right, f prime of x is, I mean, this is also fine to include as part of your solution, but it's possible to sort of circumvent having to say a whole lot about, at least about like maxima and minima. You can calculate f prime. In fact, I think that's necessary for the solution. So let's just do that. So f prime of x is like e to the minus equals e to the minus x minus x e to the minus x, right? So this is 1 minus x times e to the minus x. So this suggests that the maximum here occurs when x is 1, right? So if we just plug in 1, then we get 1 over e, right? And this is greater than 1 over pi. So already by the intermediate value theorem, we know there exists, let's say x1 in 0, 1, such that f of x1 is 1 over pi, okay? And also, like, so if you look at the expression for f prime of x is strictly greater than 0 for x in, let's say, 0, 1, like that. Or it doesn't matter, you can use the open interval. And f prime of x is strictly less than 0 for x in 1 infinity. So remember, we actually have a theorem from the section on the mean value theorem. I forget which number it is. It's like, yeah, 29.7. So by corollary 29.7, f is strictly increasing on 0, 1 and strictly decreasing on 1 infinity. So x1 is the unique solution in 0, 1 to f of x equals 1 over pi. Okay, and then for the other one, you can say like, okay, the limit as x approaches infinity of f of x, so x e to the minus x, is 0. And so there are a couple ways you could show this. The easiest one is just with L'Hopital's rule, which I'm just gonna, I know we didn't like go over it. I will say, if you feel like applying L'Hopital's rule will be useful, and I'll make this clear like on the exam, and I'll put an announcement and stuff. If you want to actually invoke L'Hopital's rule, that's fine. You can use L'Hopital's rule, the important thing is that you're actually using it as it's stated in the textbook, right? So it's stated in a very precise way in the book. You might be used to using L'Hopital's rule a little bit, sort of like, you know, I don't know, with less technical like care, I guess. So there's a very precise statement in the textbook. If you want to use L'Hopital's rule, then just make sure that you're adhering to exactly how it's stated in the book and that you've rigorously shown that it actually applies, okay? But as long as you do those things, that's fine. For the sake of time, I'm not going to like, you know, quibble over it right now. So let's just say we know this is 0. So then, you know, there exists some x, or like there exists, you know, I don't know, y greater than 1 such that f of y is less than 1 over pi, right? And then that means there exists an x2 in 1y such that f of x2 equals 1 over pi, right? And then x2 is the unique solution in 1 infinity because it's strictly decreasing, right? It's strictly decreasing on this interval, so there can't be more than one solution on that interval. Okay? Any questions about that?
Hello. I have a quite general question, which
Sure.
is what the difference is between prove and show.
Oh, I mean, there isn't really a difference. I think in practice, at least my habit is to use the word show when the statement is sort of being made in a very specific concrete context. So we're not proving like a theorem. We're not proving a general statement here. We have like a specific function and we're trying to prove that there's a specific number of solutions to a specific equation, right? So I don't know. My habit is just to use the word show, but I mean, we are proving it in the end.
Okay.
Yeah, it's just a style thing, really. Any other questions? Okay. Let's look at one more here. Let's see. So it's 6. So does there exist function? Let's see. Yeah, a differentiable function such that f prime of 0 equals 0, but f prime of x is greater than or equal to 1 for all x not equal to 0. So I think in the interest of time, I am going to, no, let's just take like, you know, yeah, let's resume at like 6:02. Okay. And then, like I said, I will take another round of like general, in case it's, sorry, I'll take another round of general questions in case anyone's thought of them. All right. So, huh. Sorry, I just thought of a thought of an interesting problem. All right. Anyway, yeah. So, what do you guys think about this? Let's see. Yeah, Sagar.
No, because it would violate the intermediate value theorem for derivatives.
Yeah, exactly. So this is no by the intermediate value theorem for derivatives, right? Because basically, if this could happen, then like no matter what, if there was any value of x where f prime of x was bigger than or equal to 1, then there would have to be, for example, a value of x in between 0 and that value of x, where f prime of the new value would be like 1/2 or something, right? That's by the intermediate value theorem for derivatives. Any questions about that? I think that one's pretty cut and dry. All right. So yeah, I'm happy to take general questions again, if anyone has thought of any. We'll try to balance things. Okay. All right. Oh man. Yeah. Yeah. So the next one was so this is problem review problem 7. So show right. So show that the limit as epsilon goes to 0 of 1/2 epsilon times the integral from x minus epsilon to x plus epsilon of f is f of x. This is like, okay, so f is, like integrable or continuous, I guess, is continuous on like AB. Oh, let's see. Oh, yeah. Oh, there's a typo in this question. Sorry. I'm sorry, guys. There is a typo in this question. It should be continuous, specifically. This actually becomes false. This becomes false if f is not continuous. So the way it's stated right now, it's integrable. It should be continuous. So sorry about that. So f is continuous on this open interval, then this should be true. So it looks pretty similar, right? This one's a little bit complicated, so I'm just going to go through it right now. It looks, or not like that complicated, but so it looks similar to what we've seen before. Like we know that like the integral from x to x plus epsilon, right, with f, 1/epsilon times that. Oops, epsilon, the limit as epsilon goes to 0, is f of x, right? That's by the second fundamental theorem of calculus, right? Let me just make double sure here. I guess it's like, okay, f is continuous on AB and integrable. Well, it's like automatically, I guess it's automatically integrable if it's continuous on a closed interval. Okay, let's just make this be a closed interval. I don't know why it's stated this way. Something weird happened. some of these problems I pulled from like an old review thing. Sorry, so it must have been back then I made this like weird typo. Let x be in the open interval AB. Yeah, this should do it. I think this should be it. Yeah. Yeah, this is definitely it. So, right. So this this is true by the second fundamental theorem of calculus, right? So if you like split this thing up here, so this is like the same thing as 1/2 times like 1 over epsilon times the integral from x to x plus epsilon of f plus 1 over epsilon times the integral from x minus epsilon to x of f, right? Then you just want to show that this approaches f of x. And this one, you can actually just view this as like, let's see. So let's look at like 1 over epsilon times the integral from x minus epsilon to x of f, right? We can view this as, so the limit as epsilon goes to 0 of this is the same thing as the limit as y approaches x of the integral from y to x of f over, let's say, sorry, x, that's like x minus y, yeah. Sorry, I was kind of zoning out. All right, so this is the same thing as like the limit as y goes to x of like the integral from a to x minus the integral from a to y of f over x minus y, right? Yeah, and that's the same thing as the limit as y goes to x. Just if you just like flip both the numerator and denominator, right? Then you get a to y of f minus integral from a to x of f over y minus x, right? And so that should be, that's also f of x by the second fundamental theorem of calculus, right? So this shows that, so this goes to f of x, right? And this goes to f of x. So overall, it's just 1/2 f of x plus f of x. So that's just f of x. Okay, I'm going to leave it at that, unless there are questions. Yeah, so the whole point is that like what we're doing is we're just taking this, limit here and we're just rewriting it until we can view it as like the derivative of the integral, basically, right? And I mean, it's already like almost exactly that. It just takes a little bit of a weird, you know, I don't know. There might be some other way of doing this where you use like the chain rule or something like that. But I kind of like this way because it just feels very, very clean or very like proper or something. All right. Anyway.
Can you go back to the other slide, please?
Yeah, sure.
Thank you. I'm a little bit confused about the 1/2 outside of the like sum that you circled. Lower down.
Yeah, I just like, so we have a 1/2 epsilon here, right? So I just wrote that as like 1/2 times 1 over epsilon times this thing, right?
And then if they each go to f of x. Oh wait, yeah.
Yeah. So this whole term goes to f of x, and this one goes to f of x. So yeah, you get 2 f of x inside the parentheses, yeah, and then the 1/2 cancels that out.
Okay.
Right. Okay. So let's go on to problem 8 here. So right. So suppose f, let's see. F is defined on negative a, and f is even. So that means f of x equals f of negative x. And suppose fn of 0 exists. Show that if n is odd, then fn of 0 equals 0. Yeah. So yeah, let's take another like 3 minutes. So we'll resume at 6:17. Oops. Okay, so there is some like a little bit of weirdness in this one. Honestly, I kind of regret not like just stating it in a nicer way, but there's some strange stuff about, okay, like for this specific value of n, so we're saying like, suppose fn of 0 exists for like some specific value of n, right? I guess I should say like, this is for some value of n, right? Then that definitely implies that like fk of 0 exists for every k less than n, right? But we don't actually know, well, for one thing, we don't know if fn actually exists for any other value except for 0. But we do know that fk has to exist on some like open interval around 0. So what we like, and it's actually kind of important that we say this. So if n is odd and fn of 0 exists, then first of all, fk of x exists. Like, so there's some like negative b subset of negative a such that this exists for all x in negative b. Okay. Specifically, this is because, right, like fn minus 1. So fn minus 1 has to exist on some open interval around 0, right? Because otherwise, by definition, fn of 0 couldn't exist, right? Because fn of 0 has to be the derivative of fn minus 1 at 0. And for the derivative to exist, then the two-sided limit of the difference quotient has to exist, right? And for the two-sided limit of the difference quotient to exist, fn minus 1 has to actually exist on like an open interval around 0, right? That's just by the definitions. That's the way we've set up the definitions, okay? So fn minus 1 exists on some open interval here, but then automatically that means that fk of x exists for all x in the same interval here, right? Okay, so we've established that like all of the first n minus 1 derivatives exist on this open interval, although fn itself might only exist at 0. Okay, so then notice that like f equals f compose u, where u of x equals negative x, right? So by the chain rule, this is on all like negative a. Well, let's just say negative bb. It doesn't matter. So by the chain rule, f prime of x is f prime of u of x times u prime of x, right? And so that's just negative f prime of negative x, right? This is for x in negative bb. I mean, it's true. This is actually true on like just wherever. This is true wherever f prime is defined. But specifically, it's true on negative bb. And then by the chain rule, again, right? So since f prime, this means that f prime equals negative f prime compose u, right? This is wherever it's defined, right? So then by the chain rule again, f double prime of x equals negative f double prime of negative x times negative 1. So that's just f double prime of negative x, okay? So f double prime is even. And then a simple inductive argument. So induction will tell us that like fk is even whenever k is even and less than n, let's say. I mean, obviously, if fn exists for like all values of n, if f is just infinitely many times differentiable, then this is just true regardless of whether k is less than n. But in our specific case, we're not actually assuming that fk exists for values of k bigger than n, right? So, but fk is even, right? And so then the same thing is true, right? For like, if so fn minus 1, right? So like fn minus 1 is even on negative b, right? So the same reasoning as before. So basically applying the chain rule, I guess I'll just say this. Applying the chain rule to fn minus 1 of 0 specifically shows that fn minus, sorry, fn of 0 equals negative fn of negative 0, right? So that's just negative fn of 0, and that tells us that fn of 0 is 0. Okay? Any questions about that? Yeah, it's sort of like awkward. I mean, I guess you can say that like fn, since n is odd, then fn is actually like an odd function. But it's sort of awkward to say that if it happens to be the case that fn is only defined at the point 0. But I mean, it is still true. So like any odd function at 0 has to be 0. So, but anyway, like fn is odd wherever it's defined, I guess, as long as it's defined on a symmetric. Well, it does have to be defined on a symmetric set, actually. All right, anyway, whatever. Yeah, let's move on. Oh yeah, this one's actually pretty easy. So show if f is an even function on R and f is weakly decreasing, then f is constant. All right, so let's take another 3 minutes or so. So we'll resume at 6:28. All right, so this one you don't even have to do any calculus. You don't even have to use any theorems, really. It's just like a basic thing of, like, about using the evenness of the function. So basically, if you kind of imagine that f experienced like a strict decrease, let's say over here, right? Then by the evenness, right, it's symmetric. So that would translate into a strict increase, which is not allowed, right? And there's like similar pictures for, if there's like a strict decrease like this, right, then again you'd get an increase like that, which is bad, right? Yeah, or obviously if there's a strict decrease over here, then you get a strict increase over here, right? And that's bad. So no matter what, right? Oh, whoops, goes the other way. But no matter what, I mean, this just isn't allowed. Okay. Any questions about that? So I'll post, like, I'm not gonna go through like phrasing this in words and symbols and stuff, but I'll post kind of a thing that has like outlines of the solutions, and that one has kind of a symbolic argument for this, in case you want to see like how to write it, I guess. Okay. Let's see. Right, so for this one, let's see. So suppose this is question 10. Yeah, hold on. Yeah, suppose f and g are differentiable on some open interval I containing some point A, and f prime of x, so f prime is less than g prime. Yeah. Or yeah, so f of a equals g of a, so f of a equals g of a, and f prime of x is strictly less than g prime of x for all x greater than a, then must we have f of x strictly less than g of x for all x greater than a. So yeah, let's resume at 6:34. All right, so let's see. So the answer here is yes. So was anyone able to do this? Did anyone do this without invoking one of the fundamental theorems of calculus?
Can you use like the IVT or whatever? Or
Intermediate value theorem.
or sorry, like the like the f of x0 is f of x minus f of a over x minus a.
You mean like f prime of x naught?
Oh yeah, sorry, yeah.
Yeah. So you're talking about using the mean value theorem.
Oh yeah, sorry. Yeah.
Yeah, that's basically right. Yeah, I think what you just said is basically the gist of it. I kind of prefer to work with the difference function just because it's a little bit cleaner. So let's say like suppose, so like if we define h, oops, so define, and that's actually exactly the right. So I'll say something about this in a second. That using the fundamental theorem of calculus here is like a little bit, or like either of the fundamental theorems, it's a little bit problematic. So define h to be g minus f, right? Then suppose h of x is less than or equal to 0 for some x greater than a. Then the mean value theorem tells us there exists an x naught in ax such that h prime of x naught equals h of x minus h of a over x minus a. This h of a is 0, so this is h of x over x minus a. This is positive. So h prime has to be positive. So h prime is positive for x greater than a, right? So that means h of x. So h of x has to be positive. Or sorry, yeah. But that contradicts this. Yeah. So any questions about that?
Could you also do this using the fundamental theorem?
Oh, right. Yeah. So not without some serious like annoying difficulty. Okay, because the problem is that like so let me think. Oh wait, actually, I guess. Oh yeah. Yeah, the problem is that we don't actually know that f prime and g prime are continuous. So so what I imagine you're trying to use, right, is like you're trying to say, so this is true, right? Fundamental theorem of calculus 1 tells us that f of x equals like f of a plus the integral from a to x of f prime, right? And similarly, g of x equals g of a plus, right, this is a plus, the integral from a to x of g prime, right? So we're trying to show that like this integral is bigger than this one, right? Right. So if you look at like, there's a theorem that looks like it might give that to us, right? Which is like theorem 33.4. So 33.4 looks promising. But if you look at the specific hypotheses, you'll see that that it actually doesn't help us here, because part 1, right? Part 1 only deals with weak inequalities, right? So part one only gives us weak inequality, right? Part two only applies, to integrals of continuous functions. And we don't actually know if f prime and g prime are continuous. So these may not be continuous on, you know, ax or whatever. Okay. Yeah. Yeah. So, I mean, so it is actually true, I think. I'm pretty sure, and in fact, I think you can use the mean value theorem to prove this. I think you can use the mean value theorem to generally prove that if there's a strict inequality, in fact, I think that's actually what we just did, basically. I think that's actually what we just did, is we just proved that if a strict inequality holds between f prime and g prime, then, or like if a strict inequality holds between two functions, basically, then a strict inequality also holds between their integrals. Yeah. If the strict inequality is true on the entire interval, like at every single point in the interval, then there also has to be strictness between the integrals. Yeah. I think that's actually what we just proved. And it's actually the mean value theorem that gets you that. So the mean value theorem is actually very powerful. Like I can't really overstate this. I hope like the homework exercises having to do with the mean value theorem, like sort of drove that point home, that you can do a lot of stuff with the mean value theorem that your instincts tell you to use integrals for, right? Like you want to use something about the derivatives to say something about the values of the function. Your instinct is automatically to like, oh, well, if I just integrate the derivative, then I can do something, right? But actually, a lot of the time, it's a lot easier to use the mean value theorem, because you can get around any like irritating like technical question about like how integrals work. Yeah, like a lot of it goes away if you just use the mean value theorem. All right. So let's see. All right. So the next one is like, suppose like 0 is less than a, less than b, less than c, less than 1 or something. Yeah. Whoa. And f of a f is a continuous function. Wait, it's actually twice differentiable, sorry. F is twice differentiable on 0, 1. Show, oh, it's prove or disprove. Okay, whatever. I don't know why I stated it that way. I'm just going to say this. So show that there exists an x such that, like an x in 0, 1, I guess, such that f double prime of x is 0. So let's resume at 6:45. Hey, sorry. I got a little bit distracted. So let's see. So yeah, this basically just follows by, and in fact, I don't totally know why they should have to equal 0. I don't think that's even necessary, really. All that matters is that f of a equals f of b, and f of b equals f of c. So I think by Rolle's theorem for like a, b, and b, c, there exists like an x1 in a, b, such that like f of x1. Oh wait, hold on. Or sorry, f prime of x1 is 0. Right, yeah. And there exists an x2 in BC such that f prime of x2 equals 0. And so then Rolle's theorem for x, well, like, I don't know, x1, x2 gives us, there exists an x in x1, x2 such that f double, f double prime of x equals 0. I think that's just it. Unless I'm missing technical detail. I don't think so. I think this is it. Yeah. All right. Oh crap. Oh man, I'm out of slides. All right, whatever. I'll have to be. We can just go back and like clear one if we need to. So yeah, let's see. The next one was right. Okay, f is uniformly continuous and absolute value of f is not bounded. Right. Okay. So suppose f is uniformly continuous on all of R, and absolute value of f is not bounded, then either the limit as x goes to infinity of f of x is infinity, or the limit as x goes to infinity. Or sorry, not absolute value of f of x. Yeah, the limit of actual f of x is negative infinity. Yeah, so take another couple minutes. Sorry, I meant to say this is prove or disprove. So prove or disprove. All right, so this one is actually, it's a little bit tricky. So this actually turns out to be false. Can anyone like describe a counterexample? Yeah, Sagar.
I guess this is similar to like the previous midterm question, but like a sign that like oscillates faster and faster, not faster and faster, but keeps oscillating and growing. So like e to the x sine
Yeah,
x.
bigger amplitude.
Yeah, as you go towards infinity, the amplitude keeps increasing.
Yeah, if you do it carefully, right? Because the point is that you don't want the slopes to get like unbound, like you don't want them to grow unboundedly, right? The slopes on the sides, basically. So something like x sine of x would actually not work, just because like it gets too steep, basically. So like no matter what epsilon you pick, eventually there'll be like a delta, or there'll be like a place where, you know, this like change happens faster than like, you know, in an interval smaller than delta, basically. But if you just make it also slow down at the same time, make the oscillation slow down, then it should work. So something like actually I think
X sine x should be fine, right? Because it'll keep.
no, this isn't uniformly continuous. It won't be uniformly continuous on R.
Oh.
Yeah, that's because it gets too steep, right? So, but here I'll draw a picture of a function that works, that's like relatively easy to define. So you can just have it be like f of x equals x at the beginning, and then have it be like, you know, f of x equals negative x, and then, or like not negative x, but like 2 minus x, and then f of x equals like, you know, I don't know, x minus 6 or something, and then 12 minus x, something like that. So you just basically keep making it be like slope 1 here, here, and like here, and like slope -1 here, 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 right? So it just keeps alternating between like plus or minus 1 slope, but it just keeps growing, like the amplitude still keeps growing over and over again, or like yeah, the amplitude keeps growing forever. This will work as a counterexample, right? And so it's like the key really is like, there's sort of a sense in which like it can't get too steep, I guess. That's not like perfectly precise way of saying it, but the problem with like x sine of x is that like, because the amplitude keeps growing but the frequency stays the same, it has to like change faster and faster in between each cycle, like over each period it's changing like faster and faster and faster. So if you chose some epsilon, like epsilon equals 1, then there's no delta that works on the entire, like on all of R, to force like f of x minus f of y to be less than epsilon whenever x minus y is less than delta, right? Because if you go out far enough, then the arch will get like so steep on the side that even in a tiny interval, like much smaller than whatever delta you picked, the difference between f of x and f of y will still be like huge, basically. So it's by keeping the like slopes of the sides manageable like this that you can really like construct a counterexample that's uniformly continuous. I think there is something you can do with sine of x, like I think you can do like x sine of like, I think actually x sine of like, maybe even x sine of 1 over x might work, something like that, because this actually slows down as x gets bigger and bigger. Yeah, something like that. I don't know. I guess it actually stops oscillating. Oh yeah, so that one actually does, no, that doesn't work, because then that actually approaches like, I don't know.
Go prove one.
Yeah, I think that one actually does approach like plus or minus infinity or something. I guess it approaches or 0. Or yeah, 1. Something like that. Yeah, it approaches 1. Sorry, what am I talking about? Yeah, so that just doesn't, that doesn't actually work. But something else like maybe x sine of like square root of x, maybe. You can put something in here that'll make it work, I think.
What about something like 0 for x greater than 0, but negative x for x less than 0?
Oh.
Like negative infinity would go
Oh,
to 0.
okay. Yeah, that's like a technical. All right, good thing this wasn't on the exam. I would have to like add in some or I would just include with these ors like limit as x goes to like negative infinity.
Okay.
X. You're right. Technically that does work. Okay. Yeah, I'm going to be doing some very careful proofreading of the exam problems to make sure this kind of thing doesn't happen.
Wait, what was the problem with that?
Oh, it's like technically you can make it so that neither of these is true because you can just have it like absolute value of f will be unbounded.
Oh, yeah, then it's more trivial.
Yeah, it's like or I could actually just change it so that it's like absolute value of f is not bounded on like 0 infinity. I think that makes it work. Yeah. So then you're sort of forced to do something like this, I think. Yeah, thank you. Thanks for pointing that out, actually. I mean, that's like, it is useful. Like, I hate when I make these kinds of mistakes. All right, so let's, I think there's only one more. So I think we can, I think we can knock this out. Yeah, this one's actually pretty interesting. I think this one's good. So I'll just go over it real quick. I'm gonna like clear. Did I just clear it? Okay. I'm gonna clear this too. All right, so this is question 13. Did I skip one or something? No, I think it, yeah. So question 13, this was, so suppose, let's see, twice differentiable at a point, f prime is 0, yeah. So f is twice differentiable at x naught, f prime of x naught is 0, and f double prime of x naught is greater than 0. Show, right? That's what it was. Yeah. So basically show that it's a local minimum. So basically show that there exists a delta such that f of x is strictly greater than f of x naught for 0 less than x minus x naught less than delta. Okay. So for this basically boils down to like eventually using the mean value theorem. So the first thing to do, so the strategy is like first show that like f prime of x is like less than 0 for x less than, well, okay. I guess I should just say first show there exists a delta such that f prime of x is less than 0 for like x naught minus delta less than x naught, and f prime of x is greater than 0 for f prime of x, or sorry, for x not less than x naught plus delta, right? So that's not difficult to do, just using the like definition of the derivative, basically, the second derivative, and then use the mean value theorem. So yeah, let's see. So by definition, there exists a delta such that for, I think, yeah, right. So for 0 less than x minus x naught less than delta, we have like f prime of x, sorry, minus f prime of x naught over x minus x naught is greater than 0, since, right, this is because f double prime of x naught is greater than 0, right? So the point is that it's like we know that the limit, right, as x goes to x naught, the two-sided limit of this is f double prime of x naught, which is greater than 0, right? So the fact that the limit here is greater than 0 means we can pick a delta around x naught that causes the values to all be positive, right? We've actually seen this exact like piece of reasoning before. We're just applying it to the first derivative now, but using the second derivative. Okay, does that much make sense? Okay. Oh, is there a raised hand?
Oh yeah,
Okay.
question. Sorry.
Oh, sure.
When which one are we fixing and which one are we choosing between x and x naught?
Well, x naught is given to us in the problem, so yeah.
Oh, okay, thank you.
So we're given that f is differentiable at x naught, or is twice differentiable at x naught, and these things are true. And then it's like, okay, x itself here is not, it's like we're saying that we can find delta so that this is true for all values of x, such that 0, like all of these values of x satisfying these inequalities, right? This is true for all of those values of x. Okay. And that's just because of that's by definition of the limit. It's because we know that the limit of, as x approaches x naught, f prime of x minus f prime of x naught over x minus x naught, that equals f double prime of x naught, which is greater than 0. Okay. So the fact that we can choose this delta comes from the knowledge that we are given the fact that f double prime of x naught is greater than 0. Okay. So we can choose delta this way. And then what happens is that, okay, so for x naught minus delta less than x naught, right? The denominator is negative. So the numerator also has to be negative, right? So that means that, so f prime of x is less than f prime of x naught for x naught minus delta less than x naught, right? And similarly, f prime of x is greater than f prime of x naught for x naught less than x naught plus delta. All right. So then what you can say is, okay, so now we claim, oh man, I'm out of space. I'm gonna just clear this too. So now we claim that f of x is greater than f of x naught for 0 less than x minus x naught less than delta. Right, so suppose x naught minus delta less than x naught, and f of x is less than or equal to f of x naught. Then the mean value theorem tells us that there exists a y in x naught such that f prime of y equals f of x naught minus f of x over x naught minus x, right? And this, or sorry, this is, wait, hold on. One second. Oh, no, sorry. What am I doing? No, we don't, it's not, we don't have to use the mean value theorem here. Wait.
We still could, right? Because then the numerator is...
Yeah, yeah, wait, wait. Oh, yeah, what I forgot about is, right. Oh, right, these are 0. Yeah, sorry. So these are 0. F prime of x naught we know is 0. I forgot about that. Yeah. Okay, so then this works. So the mean value theorem, right, tells us that, well, really, we actually have a theorem. We directly can use like corollary, yeah, because f prime is strictly less than 0. So we can use like corollary 29.4 or whatever. 29.7, sorry. Yeah, corollary 29.7. So actually, yeah, that pretty much just gives it to us. So corollary 29.7 tells us that f is strictly decreasing on like x naught minus delta x naught, and strictly increasing on x naught plus delta. So I think that, I guess technically that doesn't directly show that f of x is bigger than f of x naught itself, but it's not hard to prove that from this, because you can just say like f of x is bigger than like f of y for some y between x and x naught. And then by taking, like and then f of y has to be bigger than f of x naught. Because all of these are greater than or equal to x naught automatically because of this fact. So yeah, you can do that if you want. Or you can just directly use the mean value theorem if you don't like this way. So yeah. A direct application of the mean value theorem, maybe that's the easier thing to do. So you just say like, yeah, f of x naught, yeah, f prime of y, f of x naught minus f of x over x naught minus x. This is positive, so this must be negative because f prime of y is less than 0. Yeah. And similarly, for x naught less than x naught plus delta, the mean value theorem gives us f prime of y, some value of y where f prime of y is f of x minus f of x naught over x minus x naught. And this is positive in the denominator, so this has to be positive. So f of x is greater than f of x naught. Yep. All right. Anyway, so that's enough about that. So that does it for the review. Any final questions or concerns?
Thank you.
Yep. All right. Thank you all.
Thank
Good
you.
luck.
Thank you.
Thank you.